Okay, so let me welcome you to this fifth lecture on rollout and approximate policy iteration. And we're going to be talking about rollout almost the entire lecture. And we have covered, to some extent, deterministic problems. We're going to review deterministic rollout and discuss a little more the cost improvement property in particular. Then talk about various extensions, various variations of deterministic rollout. Then we're going to pass on to stochastic rollout and the technique of Monte Carlo research. And finally, we're going to discuss rollout for infinite spaces problems, infinite control spaces, as a prelude to our discussion on model predictive control, which is going to be in the next lecture. So remember, rollout is a form of approximation in value space with one-step look ahead or multi-step look ahead in this equation here. You see L-step look ahead, and in this equation also the problem is stochastic, which is why you see the expectation. It's the expectation over all the random variables appearing here, all the W's. And the characteristic thing about rollout is that the cost function approximation is derived by running some policy, which we call base policy. And at state xk, this is an online play algorithm. We apply it as the system is running. And as soon as we get to state xk, we do this multi-step minimization, this L-step minimization, which gives us an optimal control for the first stage and optimal cost functions for the remaining L-1 stages. Once we have that, then we pick the first component and we call it the rollout control, which is what we apply. And we throw away all the rest, all the mu's, we throw them away. Now, this process also defines for every xk a corresponding control, therefore defines a policy, mu tilde k. And we use the terminology base policy and rollout policy. So we're going to focus on deterministic rollout. We have been dealing with that case, which involves no uncertainty and the use of a heuristic, something more general than a policy. A heuristic that gives us a trajectory to complete a certain, starting from any one state, and which has a corresponding cost, which we use this notation here to denote. So we go forward from the initial state, one step at a time, until we get at the current state. We consider all possible controls, all possible corresponding next states. These are deterministically obtained from xk and uk. And then from each one of these states, we run the heuristic, the deterministic heuristic, all the way to the end. And we obtain a certain cost for this process from here to here. The cost is for a control uk, it involves the first stage cost and the cost of the heuristic running from the next state xk plus 1. And this is the Q factor. The Q factor that corresponds to xk, uk, and of course the heuristic that we are using. And the algorithm selects the control that has minimal Q factor and uses that. And then we move to the next state according to that control, and we continue, play the same game again. So the cost improvement property is very important in the context of rollout. It says that with rollout, we don't get to do things worse than with the base policy. We want to show and to operate the algorithm so that the cost of the rollout policy starting from the initial state is less than the cost of the base heuristic. And so we have a cost improvement. However, this is not automatic because the heuristic that we use can be anything, okay? It can be something completely crazy. There's no reason to believe that this cost improvement is going to hold. There are some conditions, however, that guarantee cost improvement. And one of them that we talked about last time is sequential improvement, which basically says that the best heuristic Q factor from the current state is less costly than the heuristic from that state. In terms of equations, this condition holds. At state xk, this is the heuristic cost. And these are the Q factors corresponding to the various controls. And the best Q factor, the minimal Q factor over all controls, should be less than the heuristic cost from that same state. So how do we interpret this? Okay, let's go back to this figure here. We have arrived at state x tilde k. And to arrive there, we have computed the heuristic cost from x tilde k in the process of arriving, right? We consider the Q factor that goes from here to here and then uses the heuristic. And so we have this heuristic cost. And now we are at xk, we look at all possible controls. And we find the one that gives us best minimal Q factor. And say this is the U tilde k. Then the Q factor of x tilde k uk is the cost, this first transition cost, plus the cost of the heuristic from x tilde k plus 1. So what the sequential improvement condition says is that this cost is less than that cost. And we know that there exists such a control because that's what the condition suggests. So we do have an improvement in terms of Q factor and also in terms of trajectory, starting from the initial state. Before we had this trajectory, which we call RK. We'll call it RK, and we'll call it the current trajectory. And after rollout, we have this trajectory, which we'll call it RK plus 1. So upon reaching RK, rollout has obtained the current trajectory RK. And the sequential improvement implies that the cost of RK is less than the cost of RK plus 1. So there is this monotonicity property, not only cost improvement, but also a certain monotonicity property of trajectories being generated by rollout. From R0, we go to a better cost R1, R2, and so on. There is also another property, sequential consistency, which we'll not discuss very much in this lecture, at least for deterministic problems, in which case the heuristic satisfies a stronger condition. It must be a dynamic programming policy. And it's easy to see that sequential consistency implies sequential improvement. Okay, so the main thing I want to take out from this slide is that there are some trajectories that are being generated at every step, and these have costs that are monotonically non-increasing. So now let me demonstrate this property in terms of the traveling salesman example, which we saw last time. I've changed the travel costs a little bit, but it's the same problem. It involves 4 cities with a matrix of intercity travel costs given here. We're going to do rollout with our nearest neighbor heuristic. Okay, we move from the partial tour where we are to the city we haven't visited that has a minimum travel time from the end of the partial tour. Let's trace what's happening. We start at CDA, that's the initial condition. We follow the nearest neighbor principle, okay? Nearest neighbor principle takes us down along this blue path. That's our trajectory R0. Then we move, we try to do rollout from A. And then we go one step to cities B, C, and D. And then we follow the nearest neighbor principle. From AB, I go down this path. From AC, I go down this path. And from AD, I go down this path. And the winner is this one. This one has minimum cost, minimum Q factor. So the rollout moves us here. And now we look at the two possible cities to move, and then run the nearest neighbor heuristic. There's nothing to run really because there's only one choice. And from here, we switch to here. So we started with a trajectory R0. We went on to a better trajectory, R1, and then to a third trajectory, R2, which is the final trajectory. This is the cost of the heuristic, the base heuristic, starting from X0. And this is the cost of the rollout. And there is this monotonic improvement in trajectories. Now, we want to take advantage of this property and rectify some of the difficulties that we may have with cost improvement. Let's go into variations of rollout. Here's one variation, the simplified rollout algorithm. Now we assume here that the base heuristic is sequentially improving. However, we don't do a complete minimization over all Q factors. Instead of finding the control with minimal Q factor, we use any control that has a Q factor less than the heuristic cost. Not the minimal Q factor, just any control that has a smaller, that has Q factor less than the heuristic cost. So in other words, at any xk, we choose as a rollout control any one that satisfies this inequality. Now this can save an awful lot of computation because the number of controls may be very large or even infinite, but we're considering here a finite number of controls, but it may be very large. That may involve a lot of computation. So by restricting attention to a promising subset of controls, we may be able to save a lot of time as long as we are careful to make sure that we end up with a control that satisfies this condition. Now, an important case of this type that we have already examined is multi-agent rollout. In multi-agent rollout, we don't examine all Q factors, all controls. We don't do a minimization over the joint selections of the different agents. Instead, as UK has multiple components, one component per agent, we take one component at a time. We minimize one component at a time, and we look at a very small subset of the total number of possible controls. And an important idea, which we also saw in the context of multi-agent rollout, is that even in this simplified algorithm, we still have cost improvement. Okay, there's another bullet here that says that this idea of simplification, we're going to find it in front of us later in the context of multi-agent rollout, but in other contexts when we talk about infinite horizon problems. This is an idea that extends to infinite horizon. So let's go back here to this property. This is a theorem, okay? It says that let the rollout policy under the simplified algorithm be pi tilde. So we put together these controls into a policy and let this be the cost corresponding to this simplified rollout. Then at every state, initial state or intermediate, we have cost improvement. The cost of the rollout starting from that state is less than the cost of the heuristic. And the proof is very simple. Basically, because we are careful always to follow a trajectory that has less cost than the previous trajectory, these trajectories have decreasing costs. And the first one is the cost of the base heuristic. The last one is the cost of the rollout. And this monotonicity property is maintained. It's a trivial proof to show that we have cost improvement. Okay, are there any questions? I'm sorry, are there any questions about the monotonicity property or simplified rollout? These trajectories are the same ones that we saw here, okay? So this was an example of the monotonicity property, but this example also would be true even if you did not do exhaustive minimization over the Q factors. For example, you could ignore this Q factor. As long as you found this one, you could ignore this Q factor, okay? Okay, now here's another idea involving using multiple heuristics at once on the same problem. Now, in many practical problems, there are multiple heuristics that seem promising. In fact, for some parts of the state space, some heuristics may be more well-suited than others. And it would be nice if you could switch heuristics and find the most promising and use the most promising heuristic at each state. Now, this is easy, it turns out. It's possible to construct a super heuristic which selects the best out of the trajectories produced by the entire collection of heuristics. So in this super heuristic, we are at a state, we look at one possible control, and then we just don't run a single heuristic, but we run multiple heuristics and then pick the one that works best, the one with minimum value. And we do this for every control. This is the super heuristic. And it can be viewed as a base heuristic, right? Anything qualifies as a base heuristic. And now the nice thing about the scheme is that if all the heuristics are sequentially improving, the same is true for the super heuristic. So you still have all the properties that we discussed, namely monotonicity of the trajectories generated, cost improvement, and so on. So this is a theorem now here, but the proof is very simple. Okay, so basically we need to verify that the super heuristic is sequentially improving, right? Assuming that all the other heuristics are sequentially improving. So we write the sequential improvement condition for each of the M heuristics. Here we have M heuristics, which we label 1 up to M. And this is the condition for sequential improvement of heuristic M. The minimal Q factor of that heuristic is less than the heuristic cost starting from the state xk. So this holds for every M. I can take the minimum of both sides over M. So on the right, I'm going to have the minimum heuristic cost. On the left side, I'm taking the minimum again over M, but I can interchange the order of M and U, minimization over U and minimization over M. I can interchange, so I end up with this equation. Now the right-hand side is the cost of the super heuristic, right, from xk, because the super heuristic takes the minimum cost out of all the heuristics. On the left side, we have something here that looks like a Q factor. It's in fact the super heuristics Q factor, right? Because it minimizes for a given U, it minimizes over all possible heuristics. In other words, it takes at time k plus 1 the super heuristic cost. So we have this, and this is precisely the sequential improvement condition for the super heuristic. So it's really a very simple proof. In practice, this is very powerful because, like I said, we often have several good heuristics, and we can put them together at some computational cost, of course, because we have to run all of them. But we can gain a lot in terms of cost improvement, because some of these heuristics are going to do good things in some parts of the state space, but not so good things in other parts of the state space. We get the best of all possible worlds by running all of them. Are there any questions? Okay, so now we're going to try to fix the case where there is no, we don't have the sequential improvement condition holding. We first start with a counterexample. In this counterexample, we have two stages. There's one state here, the initial state. There are two states at stage 1, two states at stage 2, and there are two controls here and two controls here. And suppose now that at x0, there's a unique optimal trajectory, okay? And suppose that the base heuristic produces this optimal trajectory starting at x0. So the base heuristic is by accident, somehow it's optimal, okay? Now, how will the rollout work? It look at this control, and then run the base heuristic from each one of these states. Now, the base heuristic has only one choice, it's going to move here. However, assume that the base heuristic at x1 star is not sequentially consistent and does not follow the trajectory that it followed earlier. Moreover, it's also not sequentially improving because it turns out by accident again that this transition here has very high costs. Now what's going to happen is that we had this cost for the heuristic at x0, and we have this Q factor, which is this Q factor, which is larger than this heuristic cost. And this Q factor is also larger than this heuristic cost because this is optimal. So the sequential improvement condition is violated. Okay, so that's what we assume. We assume that the heuristic trajectory starting at x1 is bad. And then what's going to happen is what's happening is my remote has given out. So I'll have to put a battery, but for the moment, let me finish this slide. Okay. So what's happening here is at x0, the rollout looks at this plus that and this plus that and rejects u0 star in favor of the other control u tilde 0 and moves to a non-optimal next state, okay, to this one here. So in the absence of sequential improvement, the rollout may deviate from already available good trajectory. It has a good trajectory here, but it deviates and goes down this way. So how do we deal with this situation? Well, the obvious idea is to keep track of the best trajectory that you have obtained, and then do not switch according from this trajectory unless you find a better trajectory. So this leads to the idea of fortified rollout. And as you look at this figure, I'm going to try to fix my slide advancer. Maybe I'll be able to. I'm not so sure. Just bear with me for a second. Okay, I fixed it. Okay. Are there any questions so far? You're uncharacteristically silent today. Maybe it's your mind is with the impeachment trial or something. I don't know. just a joke. So we saw in this slide a counterexample to cost improvement when you don't have the sequential improvement condition. So now we come up with this idea of a fortified rollout algorithm, which restores the cost improvement property for base heuristics that are not sequentially improved. A very simple fix, so you don't have to worry about cost improvement. And the idea is at every step to follow the best trajectory that you have computed so far. So looking at this figure, at time k, you have reached through the rollout process this state here. And suppose now that in addition to this trajectory, which is permanent, okay, we have constructed and we have maintained a tentative best trajectory. And this trajectory is this red trajectory that you see here. And it's the best complete trajectory that you have computed up to stage k of the algorithm. As you compute more and more complete trajectories, this T bar K is the best one in terms of cost. Now, at xk, we consider again all controls, run the heuristic from them, and find the control that gives you the minimum Q factor. Is this green control here? Now, this also generates a new trajectory, this green trajectory here. Now, the rule is that we adopt U tilde k if it produces a trajectory that is better than the tentative best. And then we call this trajectory, we call it the new tentative best, tk plus 1. On the other hand, if following the rollout algorithm along this green trajectory gives you an overall complete trajectory that's worse than what you had, then you just discard this rollout control and continue to use the one dictated by the tentative best. That's what this long bullet says here. At xk, we add the minimum Q factor choice if its complete trajectory is less than costly than tk, if this green trajectory is less costly than the red trajectory. Otherwise, we discard UK and follow the tentative best trajectory. In other words, we follow the red arc here, and also we keep the tentative best trajectory to what it was. And obviously, this maintains the cost improvement property, and it's very, very simple to implement. So let's illustrate this fortified algorithm. Okay, we had this initial condition, this states at the first stage, states at the second stage, and the heuristic finds the optimal trajectory at x0, okay, by accident. At that point, it gives you also the initial tentative best trajectory. So we have the best possible tentative best trajectory right off the bat. So when we run the rollout and run the heuristic from this state and from that state, even though the heuristic prefers x1 tilde to x1 star, the rollout wants to go this way, we discard this choice because it leads to a cost that's inferior to this cost here. And instead, we follow U0 star, and we keep the tentative best trajectory to what it was. So the problem of taking the wrong step here is corrected by checking and making sure that the tentative best that we do not generate a worse trajectory than the best one we had so far. Okay, now here's another application, another extension of the rollout algorithm. And this deals with a general discrete optimization problem where you minimize a cost function with n components, u0 up to un minus 1, and each component is individually constrained. Later in a future lecture, we're going to consider a rollout for the case where these components are coupled through the constraints. But for today, we're going to consider just the case where the components are not coupled. Now, the difficulty here is that we don't know the cost function and we don't know the constraints. We just don't have analytic expressions. They may be very complicated. They may be hidden in some software that we cannot interpret. So instead of G and the constraints, we have a base heuristic that does a lot of the work for us. This base heuristic at a current partial solution generate all possible next components, this U tildes, and then runs a heuristic all the way to the end and gives a complete solution, which we denote by so. Sk corresponds to the current partial solution and the choice of component k plus 1. Okay, so there is this base heuristic, which is just a piece of software that does what we want it to do, namely knows which controls to look at and knows how to run the heuristic all the way to the end. And we also have an additional software, the expert software, which tells us which one out of these complete solutions is best. In other words, this one has an internal cost function perhaps, but has the ability to rank the solutions, and it can tell us this one is best or that one is best and so on. Now, given a base heuristic that can do these things and an expert that does the ranking, we have all we need to apply rollout. We can go one step at a time and generate a trajectory, which is the rollout trajectory. So it's not necessary to have an explicit heuristic and an explicit cost function, as long as they are implicit in some software that we can use. Are there any questions here?
Excuse me, Professor. I have a question. I didn't understand the role of the expert at there. is it something that our problem or our objective, or we do not have any numerical value at here for evaluating various?
No, we don't have any numerical value. We have this expert that we input all of these solutions, and the expert tells us this is number 1, number 2, number 3, and so on. And we know how to pick number 1, the best one, right? That's all we need.
Mm-hmm. Okay. Okay. Thank you.
Of course, the expert's a computer program that has an internal way of doing the rankings, whether it's based on an explicit cost function or it's based on something else. It's something that we don't need to know. All we need to know is which one is best.
Thank you.
Okay, let me just make a little correction to this. There should be an implicit cost function, even though the expert may not be using it, so that the ordering by which the expert ranks solutions satisfy certain basic conditions, like the transitivity condition. If A is better than B and B is better than C, then A is also better than C, according to the expert's preferences. But that's all that is needed. Okay, so here's an application of this, and I was involved in this application. It involves RNA folding, and this is a reference that you can find in your class notes. It's a 5-author paper. It came out just very recently, together with 4 ASU colleagues. And okay, RNA, we're getting into very popular stuff, but this does not have anything to do with vaccines. It has to do with RNA and how it folds. Okay, RNA involves a sequence of molecules, nucleotides, and there are certain types, A, C, G, and U. And we have this sequence, which is given to us. And nature folds this sequence by pairing various types of molecules, A with U, C with G, and combines and binds the various nucleotides to each other. And it has a way of doing that, and we're trying to predict what nature will do. That's a very fundamental problem in computational biology. And it has been addressed as a dynamic programming problem since the early 80s. However, this is the first time where rollout is being applied. There are a lot of software that do dynamic programming solutions, but what rollout will do is use this available software to obtain a rollout algorithm, which hopefully is better. It seems to be better according to our results. Okay, so let me explain this figure here. A complete sequence is something that what you see here, and these arrows that you see here indicate pairings, okay? So this letter is paired with that letter. It has to be AU or GC for this to be legitimate. This one is paired with that, this one is paired with that, and so on. And we're looking, this is called a folding. After you specify the pairings, you have a folding. And now the folding should also satisfy some constraints. Okay, one constraint that people often use is that this pairing should not cross. In other words, this arc should not cross with another arc, okay? Or another arc like that. So there are some constraints on the pairings. And what we need to do is specify for each one of these molecules whether it involves a forward pairing or a backward pairing, or it involves no pairing at all. So we can do this one step at a time, taking a partial sequence as our state, a partial sequence together with partial decisions, like that here there's a pairing of that kind, here's a pairing of that kind, and so on. And then what we're going to do is enlarge this sequence by one more letter. So what does that mean? It means that, let's say, if this is the current partial sequence, we have to decide whether there's going to be an open pairing starting from here, a closing of a pairing starting here that will go backwards, or no pairing at all. So this is the state, something like this, and these are the decisions. And then there are software, well-established software available, publicly available, that given a partial folding, they will complete the folding. They will act as the base heuristic, and they will provide a complete folding at the end. And there are also other software that will do the ranking of the pairings according to some physics. Now, biologists don't quite agree exactly on how RNA, on the basis of what criterion RNA folds. So the expert, there are several different expert software that one can use. So here we are, the base heuristic, given the partial folding, generates a complete folding through this base heuristic, and two complete foldings can be compared by the expert software. And there's no explicit cost function. It's internal to the expert software, and not even the software developers know what this cost function is. It's just hidden in there. So if you give me partial folding software and expert software, I can build you a rollout and reasonably hope to get something that's better. Now, what is better is not very clear, but biologists can look at a complete folding and decide on whether it's interesting or not so interesting, and then they may try to find uses for their predictions. And since I'm not a biologist, particularly, and this is not a biology class, I'm not going to go into more details, but you can look at this paper here, and those of you that are interested in computational biology may have other applications of similar type. Are there any questions? Okay, we're moving very fast. We are going to take a break. Let's take a 15-minute break. But I have a challenge question for you. It has to do with multi-step look ahead in deterministic rollout. So the kind of algorithm that we envision here, based on our view of multi-step look ahead, is one whereby we build a deterministic trajectory, and at the end of the current trajectory, the current state, instead of looking at just one control ahead and then run the heuristic, we look at several controls ahead, and then we run the heuristic. Now, that's the basic structure, and based on the Q factors that we obtain this way, okay, for every sequence, there's a Q factor. Based on these Q factors, we can build a rollout algorithm. And my first question to you is, how would this rollout algorithm work? The second question is, what do we mean by sequential improvement in this context? How can we relate it to the concept of sequential improvement for one-step look-ahead rollout? generally, we expect that multi-step rollout will work better, although we are not entirely certain about that. But what's the main computational difficulty in applying multi-step rollout in this context? We talked earlier about simplified rollout. How would this look like within this multi-step context? Finally, we discussed rollout with an expert. How would that work in this multi-step context also? So let's take some time to look into these questions. In fact, let's take 20 minutes, and we will come back in 20 minutes, which would be 5:38 in Arizona. So, how this rollout algorithm work? How can you describe it? Anyone?
I can give it a try.
Yeah, give it a try.
Okay. So similar to the one-step rollout, so you would look at all the Q states and run the heuristics and pick whatever the minimum one is. But instead of immediately acting and moving to what that new state should be, you need to simulate this again, say like L times, where you're looking for the next Q state, you run the heuristic again, and you keep repeating this L times. And then as soon as you finish that, you choose the minimum cost or the sum of all those costs, those L costs, and then actually make your move at the end of that. Something like that.
So how many times would you run the heuristic total?
I guess L times. Not sure.
From how many states? Of course, you have to run from.
Yeah. Oh, that's true. You would have to. I'm not sure. Let's see. L times the number of states.
L times the number of states. At what stage? Okay. How about the states at the very end? Why do we need to run the heuristic from these states? We can just go here, run the heuristic, go here, run the heuristic, go here, run the heuristic, run the heuristic again.
I suppose you could.
So will that work? We're going to look at all Q factors. The Q factors here involve sequences, L-step sequences of controls, plus a heuristic cost. I'm not sure if that's exactly the same as what you said.
No, it's different, but I kind of see it now.
Okay. Anybody else about this operation? Any comments?
I guess a comment. So the total number of states that we will have, the total number of heuristics that we will have to run will be the number of branches out of xk times the number of branches out of each of the nodes that happen from xk plus 1, right? So in this case, it's 4, but it will be any possible number of combinations. And that's the number of total heuristics that we will run, correct?
Right. It depends on on the branching factor of the tree, the number of leaves, basically, of the tree.
Okay.
Each leaf corresponds to a. Okay. Well, there may be some duplications. Okay, you may get to a particular state in a number of ways, but the main thing is that you need to consider all sequences of controls, and then from wherever that takes you, run the heuristic.
Okay. And then
so there's a lot more runs of heuristic, of course, right?
Right.
But you'd expect that. That's the price for That's the main computational difficulty in applying multi-step rollout. You have to do it many more times.
And then once we select the one with the lowest Q factor, we only take the step of the first state of the sequence, right? Only of K plus
Exactly,
1.
yeah.
And then from that point, we run L steps ahead again, run those heuristics, and then do it all over again. We don't take the sequence. We only take the very first step.
That's exactly right. Yeah, it's exactly right. We run the heuristic from all these nodes, and we find the best Q factor, which would be a whole sequence from xk to the outer edge of the look-ahead tree, and the cost of that plus the cost of the heuristic. So in the end, we're going to get, instead of getting a single control that is best in terms of Q factor, we get a sequence of controls that is best. And then we use the first one, throw the others away, go one step forward, and repeat, which is what you said, right?
Yeah, that's what I was trying to say.
Okay. So what's the proper definition of sequential improvement, given that we've, okay, once we settle in the algorithm, what's the definition of sequential improvement? Remember, sequential improvement compares a heuristic from where you are with the best Q factor, right? So we talked about these Q factors involving multi-step control sequences. How about sequential improvement holds if I can find some Q factor here that has cost that's less than the cost of the base heuristic from xk? That will work, right?
Right. So sequential improvement will be the minimum over a sequence of states of Q factors should be less than or equal than the heuristic being used.
Exactly, yeah.
Okay.
Each Q factor corresponds to a sequence of controls, not states, controls. And take the minimum over all sequences, and then that should be less than the cost of the heuristic. And now the important thing is that once you have that Q factor that is better than the cost of the heuristic, you can follow that trajectory from xk forward and do better than the trajectory of the heuristic. In other words, we have a monotonicity of trajectories kind of result, except that the trajectories involve multiple controls, not a single control at every state. Okay, if we accept that, what would the simplified rollout algorithm look like? Assuming sequential improvement as I have defined it.
Would you start computing the costs of these trajectories and just stop once you found one with a cost less than the heuristic?
Right, yeah, that's one way to do it. Although it's not clear, but it's not the only one. But basically, you just find some control sequence that leads to a Q factor that's better than the cost of the heuristic. Now, you may stop at the first one, or you may try harder to look at a promising set of trajectories that take you from xk to the edge of the tree, and then assuming that you have found one that's better than the heuristic, then you take the best one of those. Basically, simplified rollout means you simplify the look-ahead tree. Just prune it, okay? Prune parts here, prune other parts here. That's simplification. You simplify the number of control sequences, and you can stop as long as you find one that does better than the best heuristic. Is this clear? Simplification is something that a lot of people do in multi-step look-ahead in all kinds of contexts. You just prune the look-ahead tree so that it's not so bushy and not so time-consuming to explore.
Kind of like alpha beta pruning algorithm is something similar.
Alpha beta pruning is a principled way to do pruning in two-player games, okay? Here we're talking about pruning in a single-player situation. Alpha beta pruning is based on the minimax on games of, zero-sum games like chess or Go, two-player games. And I can't explain alpha beta pruning here, but it certainly involves pruning, but the principles of the pruning are different.
Okay, yeah, understood.
Okay. How about rollout with an expert? This seemed to mystify you, and indeed is a little mystifying. How can you get rid of the cost function? How can you get rid of the structure of the problem? But as long as someone knows it, as long as you have a base policy that knows the structure and an expert that knows how to rank solutions, is perfectly fine. So how would rollout with an expert work with a multi-step look ahead? What kind of base heuristic would you have, and what would you require to do? What kind of expert would you have? Okay, the expert doesn't change, right? I mean, in the end, you have to, the expert is capable of ranking full trajectories, or full trajectories. So, okay, this has nothing to do with single step or multi-step look ahead. The expert will work the same, but the base heuristic should be capable of generating the look ahead tree, not just the next controls, but generate the whole look ahead tree and also be able to run the heuristic to the end. Okay, any other comments about multi-step look ahead?
So on the last part on rollout with an expert, the heuristic, it's independent of the expert, right? We can still come up with our own heuristic that we believe finds the Q values, and then at the end the expert is going to provide its own ranking, and then we use that as the solution to select the next state, right? But at least from the example that you showed us earlier with the RNA, you have some piece of software that run the evolution, the heuristic, and then another piece of software that did the ranking, and those two may not be looking at the same values. So those two don't have to be related, right? Like we could try and design our own heuristic to evolve the sequence.
That's right. They can be totally unrelated. And in fact, there are several different experts that you can use, which are interchangeable as far as the algorithm is concerned. You take out one piece of software and put another one in its place. And similarly with the folder, the base heuristic, there are several folding software for RNA that are available to the public, in fact, as well as commercial. And you can take one out and put another one in its place and see what works best for the kind of sequence that you have. It requires a little bit different mindset than people in control and decision control, operations research, and even artificial intelligence are used to, because the problem is ill-defined to begin with. it's not clear what a good folding is, okay? Biologists disagree about what is a good, what is the best folding on or the optimal folding. But they can recognize interesting foldings. So they will put in there different experts and see what happens, and then look at the results, and maybe there's something interesting that one can obtain. It's a little bit of a different game than what a lot of us are used to.
I see. Thank you.
There's one comment I want to make before we leave this this slide, which is the following. I think I made this point at an earlier lecture, that multi-step look ahead is really a special case of one-step look ahead. It's just a question of where do you start the heuristic, the definition of the heuristic. So this is two-step look ahead involving this heuristic. But suppose I start the heuristic right here, okay, and call heuristic the last stage plus the heuristic, okay? From then, that would become one-step look ahead. So here, it involves optimization, of course, right? So the heuristic from this state here would be optimization of these two plus the ordinary heuristic. So if you take this point of view and you take and view multi-step look ahead as one-step look ahead, but with a different heuristic, then you can apply all the discussion for one-step look ahead to this particular context and get a lot of insight and answers this way. Does this make sense? Okay.
Yeah.
So we're leaving this slide and go to stochastic rollout and Monte Carlo research. Okay. Now in stochastic problems involving rollout, again, you have one-step or multi-step look-ahead minimization. You have approximation of you have an approximate cost function at the end that's derived from some base policy. And you have this minimization, one-step or multi-step, which defines the rollout control to apply at state xk and the rollout policy. The only thing that's different is the expected value here over the uncertain quantities. And we're going to focus on the case where this expected value is not calculated in closed form, but rather is calculated by Monte Carlo simulation. If you use Monte Carlo simulation also, it's not only this expectation over this expression here that you are considering, but also you can calculate the cost of the base policy from the state, the final state of this look ahead, by simulation again. So simulation is used both for the L steps and also to calculate the values of the cost values of the base policy. And now that's a big problem. That's because this Monte Carlo simulation takes a lot of computation. Okay, so now back to the definition. There is a certain cost improvement result, which says that if the base policy is a legitimate policy, it's sequentially consistent, and that's the only kind that is worth considering in the case of stochastic problems. So we have a policy that gives an action, a control for every possible state and stage, and you use that to generate these cost function values. If you do that, then you have cost improvement. Starting from any state and any stage, the rollout policy has a smaller cost than the base policy. And the proof of this is essentially the same induction proof as for the deterministic case, which I think I gave in the previous lecture. So you do have some, you don't have this cost improvement property. Of course, this assumes that there is no truncation, okay, and no terminal cost approximation. So it holds under some idealized conditions. Also, this approximation, this value is not going to be exact because of simulation error. So in practice, this cost improvement property holds within some error bound, which is not easy to calculate. Now, the big issue here is how do we save in simulation? Because the simulation here is daunting for every possible control. And let's even focus on one step look ahead. For every possible control, you have to do Monte Carlo simulation, lots and lots of sample trajectories to average, okay? And it's easy to see that this simulation can be very time consuming. It can be parallelized if you have Monte Carlo simulation is very well suited to parallelization, having parallel hardware. On the other hand, it's still a lot of computation. So that's the big issue here, and we're going to focus on that. But first, let's look at an example, an application, the original rollout application, so to speak. It involves a game of backgammon. I talked briefly about that in the first lecture. Backgammon is a game of skill and strategy, and also chance, because it involves rolling the dice. It involves two players, the black player and the white player, which have these pieces here on the board, and they move in the opposite directions. And okay, there are certain rules that guide the movement, and also when one player wins over another. There's no draw here. Either one player wins or the other player wins. There's no tie. What is the state here? Well, prior to every movement of pieces, there's a roll of the dice by either the black player or the white player. So let's assume that we are at the white player's turn, and the state is the board position and also the roll that this white player has rolled, okay? Like 6 and 4 or 1 and 3 or whatever. Now, given the roll of the dice and the board position, we can generate all the successor positions, all the possible successor positions that correspond to different ways of playing the role that you have. And now Tesoro's idea was, from each one of those positions, run Monte Carlo simulation with some backgammon player, roll out the game. That's where the word rollout came from. Roll out the game, but this is a game of chance. So the rolling out had to be done with Monte Carlo simulation. There is a cost of +1 or -1 only at the terminal position when one player wins or loses. There are no intermediate costs. So you got to run all the way to the end, the game, and then average the scores, and that gives you a number. That number is the score of the position. It can be viewed as some kind of probability of winning from that position. And the algorithm selects the play that leads to the position of highest score for that player. That's the way the Tesoro scheme worked. And the player that was used to roll out the games was another program called TD Gammon, which was an earlier program that Tesoro had developed based on approximate policy iteration and a method of temporal differences, which we will not explain in this lecture. So there was a neural network that was trained to generate moves at given positions and roles, and that's the TD Gammon player, and it was used to roll out games for both players, for both sides. Also, because some of these trajectories to finish the game were kind of long, truncation was used at the rollout. And the truncation involved cost function approximation at the end, which was again provided by TD Gammon. Now, TD Gammon played a pretty decent game, not quite at the level of world champion, but close to it. But this rollout played much better. Okay, it was extremely good. In the backgammon community, in fact, people think that a rollout player is the optimal player. That's not true, okay? It's still suboptimal, but it plays so well that people think that it is optimal, exactly optimal. Now, the problem with the rollout backgammon player was that it took an awful lot of simulation time. So for a given roll, there may be like 20 positions or so, okay? I'm guessing here, 15, 20, 30 positions that are possible. And from each one of those, you have to run hundreds of games, okay? And that's a lot of Monte Carlo simulation. And given that this work was done in 1996, it took an awful lot of parallel computing power to get any results. Even now, I could not find a rollout player on the internet that, that could play sufficiently fast to have a game with you. There are a lot of players based on neural networks, like the TD Gammon, like the sons of TD Gammon. There's several of those on the internet, and you can play against them. And they will generate moves in seconds, almost instantly. So that's the backgammon example. Very impressive at that time, very motivating, and also highlighted the difficulty with excessive simulation time. Now, Monte Carlo tree search is one of the methods that can be used to alleviate the simulation problem. One way to reduce the simulation requirement is using truncation, okay? Monte Carlo tree search is a different way to do that. Any questions? Okay, the motivation is to save simulation effort. So far, we have assumed that equal effort is made to evaluate the Q factors of all controls at a state xk, equal amount of simulation. In fact, in Tesoro's program, it was an equal amount of simulation. The number of trajectories was the same for all possible plays. On the other hand, we may try to be more clever than that. In particular, some controls may be clearly inferior to others and may not be worth as much sampling effort, as much simulation. We may not need to calculate the Q factors of these controls very accurately, because after a few simulation runs, they look so bad that, okay, we don't want to bother with them. Also, we may have some kind of heuristic criterion to decide which controls are clearly inferior. So that's one game that we can try to play. Also, just as some controls can be clearly inferior, some controls may also appear to be promising. On the basis of some limited simulation, they seem to have nice Q factors. So they're promising, they may be worth exploring better through the use of multi-step look-ahead. Okay. So that's another idea involved in Monte Carlo tree search. It can be viewed as a randomized form of look-ahead, where we explore the look-ahead tree with different, based on some kind of randomization, based on some criteria. In particular, adaptive simulation is a term that's being used here. Simulation effort that's adapted to the perceived quality of different controls. That's what adaptive simulation refers to. And in doing adaptive simulation and exploring some controls more than others, we may try to balance exploitation and exploration. This is a classical trade-off that people talk a lot about in reinforcement learning. In this context here, exploitation refers to extra simulation effort on controls that look promising. Try to exploit the potential of these controls. Exploration refers to exploring adequately the potential of other controls. For example, we want to make sure that we don't neglect any controls that may look on the surface to be not so good, but on closer examination, they may turn out to be more interesting. And if we were to do more exploration, then we might discover their potential. So that's you have a thumbnail, some of the basic characteristics of Monte Carlo tree search. And let me also make one more point, because there's a lot of confusion in the literature about that. People think that Monte Carlo tree search improves performance. That's not what it does, at least in the context we are discussing here. It just tries to save in simulation effort. Of course, if you save in simulation effort, that means that you can devote more effort to other parts of the algorithm. So in that sense, it may improve performance. But by itself, the best performance out of rollout is obtained by doing exhaustive simulation. The more simulation you do, the better Q factors you're going to obtain, and the more informed decisions you're going to be able to make on the basis of these Q factors. Okay. So let's look at this landscape a little closer. Let's look at one step look ahead. At the current state, we consider various controls. Here in this picture, we have 3 controls. We simulate sample trajectories to the end. These are sample Q factors. And these are samples of this expectation here. For particular state control pairs, we obtain a sample, okay, by simulation, a sample of this. If we get enough samples, we can average them and get a close approximation to the expected value. So let's assume now that there are a finite number of control elements. We'll denote them by 1 up to m. And suppose that we simulate trajectories here, and each time we decide we're going to simulate this control, or we're going to simulate that control, or we have neglected this control, let's simulate that, okay? How do you decide which control to simulate? So suppose that after the nth sample, the nth sampling period, we have QUN, which is the empirical mean of the Q factor of control U. Now, what does that mean? This means value of Q factor, total sample value, divided by total number of samples. So it is the running average of Q factors corresponding to U and the state that you are, okay? Now, we want low values of that. If this value is low, that indicates that U is a good control. And we view this as an index for exploitation, an index about the potential of control U, a numerical value. So we do the simulation and we get exploitation indexes for these controls. Some of them are going to be high, some of them are going to be low. How do we use these exploitation indexes, the running indices, to select the control that we're going to sample next? That's one of the things that Monte Carlo tree search does. It decides which particular control to explore with simulation. And one way to do that is on some kind of statistical test. Bear in mind that none of this is very precise. There's a lot of voodoo stuff that goes on here in this area. And people will draw conclusions from one problem and apply them to a different problem. But this scheme that I'm going to describe makes sense and is also widely used. So, from the previous slide, we are at a given state. We have generated n samples, and we have exploitation indices for each one of these controls. However, the problem is that some of the other controls that may have bad exploitation indexes may not have been explored sufficiently. They may not have been allocated a sufficient number of simulation samples. So Monte Carlo tree search tries to balance the two: sample controls with a small sample count and sample controls that seem most promising. And a popular strategy is to introduce, in addition to the exploitation index, an exploration index, which indicates to what extent a particular control has been, the control U has been sampled, has been explored. And people have different formulas for this exploration index. The formula for the exploitation index is pretty clear. It's the running average of Q function values, Q function samples. The exploitation index, a lot of people have different proposals. And there are statistical considerations, statistical tests, confidence interval type of tests. And the RUN depends on the sample count of control U, and an analysis that figures prominently in this area is the analysis of multi-arm bandit problems. It's a particular type of dynamic programming problem where the trade-off between exploitation and exploration becomes particularly vivid. And for arm bandit problems, people have developed rigorously a rule, a confidence interval-based rule for setting the exploration index. This is called the UCB rule, upper confidence bound. And the formula is this expression. Depends on the number of samples. It depends on SU, which is the sample count of control U. And it depends also on a constant. And the multi-arm bandit analysis suggests C equals square root of 2. However, people play around with other values also, assuming normalization. There are a number of rationales here for selecting C and also for this formula. Upper confidence bound rules have been extended to multi-step look ahead. There's another rule called UCT, upper confidence tree bound, something like that. However, AlphaZero uses Monte Carlo's research and does not use any of these. Uses something different, again based on heuristics, semi-heuristics, some things that make sense, some that are kind of voodoo, mysterious. I would trust, of course, the alpha zero rule very much because of its apparent success. But why they have picked this particular formula, which you can find in their paper, is not very clear, nor do they explain fully. Needless to say also that this formula here, this UCB rule, is based on multi-arm bandit problems, but it's applied to other problems that are not multi-arm bandit, that have different characteristics. So is this legitimate? Okay, seems to work for many problems, but I would also not be very trusting in the validity of these rules here, or that they represent some kind of absolute truth. In reality, Monte Carlo tree search works very well for some problems where it's well suited, but there's no guarantee that's going to work on your problem. So trust but verify is the motto here. Are there any questions? There are some other issues in stochastic rollout that we have not discussed, and you can find the discussion here and there. There is here we said that this expectation is obtained with Monte Carlo simulation. But in Monte Carlo simulation, there's a significant issue having to do with variance reduction. The average that you get based on simulation samples may have large variance or small variance. How you do the simulation can play a big role in reducing the variance. And you can save simulation effort by using variance reduction techniques tailored to this context of stochastic rollout. We're not going to get into the details, but I want you to be aware of the fact that there's more than meets the eye and that we have covered in this field. And with that being said, I'm going to go to the last topic, which is a different kind of problem, infinite spaces problems, including infinite control space. And these are the kind of problems that arise in control theory, control applications. In the classical control problems, the control spaces and the state spaces are continuous, typically vectors in Euclidean space, and they evolve according to a discrete time equation or a continuous time equation. Two of the most prominent types of control problems are these: the regulation problem and the path planning trajectory following type of problem. You may have seen this particular example. It's very popular, particularly in academia, but you can also try it yourself by balancing a stick on your finger and or in this particular picture, balancing a pole that has a mass at the end in the upright position by moving a car to sort of compensate for the moves of the pole, the tendency to fall over this unstable equilibrium at the upright position. So if the upright position corresponds to the origin, a zero of the problem, okay, the control is the force that you apply on the car, And there is a systems equations that you can write here, differential equations. And there's an interesting control problem. It's interesting not because it has many applications, but because it's kind of cute and easy to understand and still quite complicated. So that's an example of a regulation problem, keeping a system around the origin or around a set point. Very, very common problem that dates to more than 100 years, since Maxwell's time, actually. Another problem is instead of keeping the state of the system near the origin, keep the state of the system around a given trajectory, or even designing the trajectory like an automobile wants to move from point A to point B, but there may be some constraints. The constraints may be velocity constraints. It cannot run too slow in some places, or too fast because it will get out of the track. There may be acceleration constraints, and there may be obstacles, like it has to stay on the road. And there may be moving obstacles also, something that's particularly vexing and requires online replanning, right? And there are these constraints, state constraints and control constraints. And the classical formulation of linear quadratic problems does not deal very well with state and control constraints. So that has motivated alternative methodologies. In particular, model predictive control has the ability to control systems while respecting state and control constraints in a reasonably efficient, computationally efficient way. I think I mentioned, I covered model predictive control in lecture 3. I'm going to discuss here just the principle on which model predictive control is based, and we're going to come back again to it in the next lecture. It is a general principle for dealing with deterministic infinite spaces problems, including infinite control space. So let's suppose that the system is running, we are at a state xk, and we're considering what control to apply out of the infinite number that is available. Now, the fact that control space is infinite means that the number of Q factors is also infinite. So we have to compare an infinite number of Q factors as well as compute them. Now, one possibility is to discretize the control constraint, but to do a good job of discretization may require a very large number of Q factors, so that may be inefficient. Now, here's the other possibility. Instead of discretizing and using some kind of heuristic in the context of rollout, it's possible to use heuristics that are based on optimization and look L-1 steps ahead. In other words, consider here a base heuristic that involves minimization over L-1 stages. So this is the base heuristic, an optimization problem that involves L-1 stages. And now you have also optimization of this cost of transition over UK plus the heuristic. So you can lump together, you can combine the base heuristic minimization, which is L-1 stages, with the first stage minimization, which is one more, for a total of L stages minimization. So a form of rollout involving a minimization heuristic is to look forward L steps and do a continuous space optimization over control sequences within this horizon. And we combine the Kth minimization and the optimization heuristic into a single deterministic optimization. And now how do you solve this optimization, this L-step optimization? Well, that's what nonlinear programming does well, deal with continuous spaces over a limited number of stages. And that's what people have been using in this context, as well as in model predictive control. Use some kind of a quadratic programming formulation that takes into account the state constraints and the control constraints, as well as the dynamics of the system. There are gradient methods, conjugate gradient methods. There's a very well-developed algorithmic theory of optimal control problems that dates back to the 60s, okay? The 60s and even before that, which was developed in parallel with dynamic programming. In the 60s were a very active period for optimal control. You may have heard of Pontryagin's minimum principle. All of this research was fueled by the space program, getting a man to the moon, and getting spacecraft and satellites in orbit. All of this involved optimal control methods involving continuous spaces that were basically involving vehicle dynamics, Newtonian dynamics, which are, of course, continuous space formulations. So this methodology has been available for a long time and is still very, very potent and very useful today, and has been used in this context for solving these continuous spaces problems. And that's the idea that underlies model predictive control, and we're going to get to that in the next lecture. So that's the end of today's lecture. Are there any questions?
I don't have a question. I have a comment. It seems that the latest version of the lecture notes, the images are not showing, the figures are not showing, it's only the text.
Okay, good. So I'm going to correct that. I'm going to post the latest slides and the latest lecture notes. So look in an hour or so and they will be there.
Thank you.
Sure. Okay. So next time we're going to cover model predictive control. We mentioned it's very closely related to rollout, and we're going to explore that relation further. We're going to look at the variations of model predictive control, the issue of constraints, state and control constraints. And then we're going to look at rollout for multi-agent problems. And that will take us a full lecture. I'm not going to announce any homework, but I will announce a homework next week. These homeworks, as you have figured out, I'm sure, are toy homeworks. They're basically designed to steer you to the right, to reading the class notes. But next week, I'm going to assign a homework that's a little bit more substantial. Finally, there's a lot of material that you can watch or read, and this video lecture is relevant to the next lecture's material. Are there any questions?
Yeah, Professor, I have a question.
Okay, go ahead, whoever wins. Yeah, go ahead.
So you mean there's a model predictive control. Are you saying that the model is already known, such as for that car, that the mass of the sphere is already known, so you may assume that.
Okay, the name model predictive control does not relate to the existence of a model. I'm not even sure what model predictive control relates to, just a name. We are going to assume a model, okay, that the model is known, if that was your question. But this has nothing to do with the name model predictive control.
Okay, so you just assume that when you apply the control signals, so the state of the system is already known, right?
Ah, okay, yes, I do.
Okay.
Yeah,
okay.
there's no methodology of model predictive control that works without knowing the state of the system. However, there are approximations. A lot of this methodology that assumes that you know the state of the system is applied in practice by replacing an estimate of the state for the real thing, okay? In other words, you have an estimator running in the background, which estimates the state, and then it uses that estimate as if it were the exact state. So model predictive control is sometimes used in that way. But the theory of model predictive control requires that you know the state of the system.
Okay, thank you.
Okay. There's another question?
Yes, Professor, I have a question about the previous slide, the rollout. I think it was in the continuous space, if I don't make a mistake. In the discrete problem, I could understand that we have a base heuristic, and then with rollout, we go one step ahead and then run the base heuristic, and under certain circumstances, you will get a better result. What I cannot see at here, maybe I will get my answer in next session, is that you said that we have this base heuristic, which is in blue, and then we can run this base heuristic, which is continuous optimization to find our answer, and somehow combine state K with the base heuristic. But then what is the advantage? We are solving a continuous optimization at the end. I mean, I could easily see what rollout is doing in the discrete form, but what I cannot see it here.
Okay, you're right that the overall problem is continuous optimization over a number of stages. And here you have continuous optimization over L stages, but the number of stages may be much smaller. In other words, L may be much less than N, the horizon of the problem, right?
Mm-hmm, mm-hmm.
Is that?
Yeah, I got it.
Okay, that's the idea, yeah.
Mm-hmm. Thank you.
Okay, good. Any other questions? Okay, guys, so we're done for this lecture. I'll see you next week.